Good morning to all of you, and it is my great pleasure to come here and address this great seminar on India's first energy festival, EnVision. So my earlier speaker, Dr. Nag, had made my job very easy by talking a lot of things about steel sector. And like all other industries which are responsible for very huge emission of carbon dioxide emission, steel industry is also one of them, and you can say that it is one of the major industry where there lies a huge potential of decarbonization. And just within the limited time frame, I will try to cover a few of the important things in this particular area, but if time does not permit, then I will also skip a few of the slides, and we may discuss later on. So, what are the driving force to decarbonize steel sector? As we know that steel sector is responsible for generating huge volume of carbon dioxide emission. About 3 billion tons of carbon dioxide every year is being generated by steel sector, which amounts to about 8 or to 9% of global CO2 emissions. And it will further increase in the coming future because as the demand and the production of the steel will increase, and especially for India, basically it is, or India like other countries also, who are likely to develop, because steel is a basic engineering material and that one has to produce in a very huge quantity in order to attain the level of a developed country. So basically in the coming future, these emissions are going to increase further. Now the second important point is that coal is the major source of energy in iron and steel making all across the world. It is not that because we should not use the coal because it is containing carbon. It is not a reason, because it is at a cheaper price and it is available in abundant quantity. And as we know that industries are running on the cost considerations, on the economic criteria. For example, many people who are here from steel industry, they know it very well that still today in India, very huge amount of DRI is being produced by rotary kiln approach. And in fact, the rotary kiln efficiency is, and you can say that emissions are on the much higher side as compared to other DRI route, but still huge amount of iron is being produced by rotary kiln. And that consumes almost the similar volume of coal. And you can say that for producing 1 ton of iron is it emits about you can say 20, it consumes some 20 gigajoule of energy for producing 1 ton of iron in the rotary kiln, and it emits huge amount of carbon dioxide, but still it has been used. And like any other industrial sector, as we know that steel industries are also trying to adopt all possible ways of decarbonizing their production. And like one of the alternate approach could be application of CCUS, carbon capture, utilization, storage. But this hydrogen is also one of the useful fuel which can replace carbon in steel industry also as well. But provided that it is available at a cheaper cost, provided that it is coming from some of the source which does not consume carbon. So as we know that hydrogen reduction is, you can say, it is one of the most promising way to produce steel in the next and far future. And as we already know, and it has been researched you can say that by a lot of progress of a lot of scientific research also, it has been proved that hydrogen offers better solution, better possibility, and better way of reduction of iron oxide from thermodynamic and kinetic perspective also as well. And if the green hydrogen is available in abundant quantity in the coming future, we can decarbonize steel sector very quickly and very easily, as we are talking about the other sector also as well. So basically, I will not just talk about it much detail because my earlier speaker has already talked. So there are two possible routes of steel making, iron and steel making. One is starting from the basic material, that is basic raw material, starting iron ore, coal, limestone, and another is that which is using the recycled scrap. With the basic route, there are two prominent routes of iron making. One involves the smelting process, another involves the DRI route. Okay, so there are two routes. One is through the smelting route, which involves blast furnace, BOF, secondary steel making, continuous casting, and then followed by the rolling mills. And another route which involves the DRI route, followed by the electric arc furnace and secondary steel making. And also in the electric arc steel making, it can also consume recycled scrap also, as well as the BOF process can consume recycled scrap up to the limitation of the heat balance that could be of the order of 10 to 15%. So if we look at the major steel production pathways across the world, we will find that still today this blast furnace route is, you can say that one of blast furnace BOF route is one of the dominating process route which is accounting for major CO2 generation by the steel sector. Although in the coming future the secondary route which will involve electric arc furnace route will dominate, but that is subject to the availability of the scrap which will be available in the coming future as the steel production goes further. Now, this is very important slide. As we can see, the global trend of the steel production is starting from last several years. And as we see that steel production is increasing continuously, and as well as the energy emission that is mentioned in, you can say that metric tons of equivalent oil, that is also increasing over the years. Although the technologies which are running in the steel sector are getting mature over the year, that means that if you talk about the blast furnace process way back in 1970, you will find that the coke rate used to be enormous, that they used to be some 900 or 800 kilograms per ton, whereas today the coke rate, and you can say that the fuel consumption has come down to a level that it is almost running very close to the thermodynamic limitation. But the volume and you can say that the demand is increasing over the years, and it is likely to increase further in the coming future. So that is also putting a huge challenge on the part of the emission, too much emissions of carbon dioxide over the years. So that we need to take care, and that we need to look for the alternate ways of using either non-carbon containing fuels or mitigating the carbon dioxide emissions by adopting alternate means of CCU or CCUS. So basically the current, you can say that current steel production is of the order of 2 gigaton per year, and current energy emission is of the order of, you can say, around 900 million tons of oil equivalent. So if you convert it in terms of total energy consumption by steel sector, it is coming around 40,000 petajoule per year. Okay. So what are the key challenges which steel industries are facing today? As our earlier speaker has told that that Indian steel industries are facing with the problem of iron ore, that on the raw material front. So the first and major challenge is that there are depleting resources of quality raw material and their increasing cost. That means that our Indian iron ore, which is high in alumina, and in the coming future, its Fe value is also coming down. So that means that today the iron which contains 60 to 61% is considered to be the good iron ore. But in the coming future, we are bound to produce steel by using even very, very lean quality of iron ore, and we need to think about the ways and technologies in order to beneficiate them. Otherwise, we will not be able to sustain such a huge demand of production in the coming future. Then also, steel industries cannot run by emitting too much volume of carbon dioxide. Also, there is a shortage of land in India because the huge amount of waste is being generated. So unless until we think about recycling and utilization of that waste, this sector will not be sustainable. At the same time, the population of this country is also too large, and there is a great demand of land also. So basically, we need to develop the process which can be, or industries which can be accommodated with the shortest available land. Also, over the last several years, the cost of coal is increasing, the cost of electricity is increasing, and also it is very much difficult to maintain the profit margin by steel industries. So that also, prohibits them to apply any kind of carbon, mitigation efforts. Like, for example, if they want to apply CCS or CCUS, that is going to cost huge, you can say that huge amount of money. Also, if they want to use hydrogen also, so unless until the hydrogen is available at a cheaper cost, this cannot work. So basically, there is a pressure to minimize the energy consumption by the steel sector, because as we know that energy cost is about 30 to 40% of the total cost of the production. And it is also important that the energy source which we are talking about, that alternate energy source, for example, hydrogen, that can be replaced only if it is if it is economic and cost effective. So basically, at the current time, this energy consumption is directly related to the CO2 emissions, because the coal is the predominant fuel that the steel sector consumes. If you look at the steel production over the years by various countries, we find that the last year, out of total around 2,000 million tons of steel production, the more than 50% of the steel is being produced by China. So China and India, basically, they alone contribute more than 50% of the world steel production. And in fact, in the coming future, it is projected that about India and China combined will be producing some 80% of the steel because this India production will rise to 500 million ton, 600 million ton by 2040, 2045. And in fact, China will always, I mean to say, it will almost come down because it has already stagnated at a certain level. So basically, since more and more steel is supposed to be produced by India and China, so whatever efforts on making this sector green, that has to be thought and that has to be implemented by these countries only. So this is, you can say, that the relative position of steel production across the world, and as you can see that China and India are the dominant one as compared to the rest of the world. Now, if we talk about the energy and CO2 status of the steel industry, as I already told that the steel industry contributes 9% of the global energy consumption and 7 to 8% of the, or around 8% of the total global CO2 emissions. These studies were performed by Professor Richard Fruyan some times back, and they have calculated the benchmark calculations for various process routes, and the theoretical minimum value for hot metal production by blast furnace route is around 10 gigajoule. And you can say that practically it has been achieved to the 10.4 gigajoule. So basically the iron producing step can use maximum energy and generate maximum carbon dioxide. And basically that is why there's a greater scope of mitigating CO2 reduction and energy and reducing the energy consumption at this iron making state itself. Although the DRI route is having slightly lower consumption of the energy and lower emissions of the carbon dioxide, but this blast furnaces are still, you can say they are one of the dominant route of iron production. So basically all possible efforts of this hydrogen mitigation are being done only on the blast furnace, as spoken by the previous speaker. So basically, if you look at this CO2 emission by various process routes, we can find out that this smelting route, that Corex blast furnace BOF, is going to have some 3 tons of CO2, 2.5 to 3 tons of CO2, that is the highest one, and it is followed by DRI and EAF route, and it is followed by, you can say that top gas recycling blast furnace, high smelt, and scrap plus electric arc furnace is having the minimum one, but provided that we are having abundant quantity of scrap available which can be recycled. Now, what are the decarbonization measures possible by the steel sector? One of the possibilities is that use of hydrogen. But if the hydrogen, if it is coming from the carbon consuming power plant, and if the energy is being used by the power plant, which is already using a lot of coal, then it will not help. So if the green hydrogen is available, then that can be used as a replacement for carbon, because the end product is water. So basically, this hydrogen usage is having the potential of reduction of carbon dioxide emissions by 80%. One of the way that hydrogen can be replaced in the DRI SAT furnace in iron making is that it can be replaced to the 100%, whereas in the blast furnace it can be done only to a limited extent. And hydrogen can also be used and it can be generated in the form of the syngas, which can come from coal gasification, or you can say that cracking of hydrocarbons or natural gas. So just a few aspects on the thermodynamics of this reduction of iron oxide. As we can see that iron oxide reduction is a step-by-step process, that the first Fe2O3 is getting reduced to Fe3O4, and it is again getting reduced to FeO under the combined influence of carbon monoxide and hydrogen. If we look at the stability diagram of this iron oxide and its subsequent state of reduction under different percentage of carbon monoxide and hydrogen, we will find that reduction of iron oxide by hydrogen, since it is endothermic in nature, so the utilization efficiency of the hydrogen is more at the higher temperature, whereas the utilization efficiency of carbon monoxide is lesser at the higher temperature. So basically these are the trends which are visible by this thermodynamic plot. So this can give you the idea about replacement of hydrogen or replacement of you can say that alternate fuel which contains hydrogen in the DRI making and in iron making in general. So and if you look at this kinetics of reduction of iron ore by the hydrogen, basically it involves a combination of the steps where the one step is involved which contributes the mass transfer control kinetics, and also the combination of another step contributes towards the kinetics control by the chemical reaction. So basically, this is a simple example which is giving the topochemical nature of the iron ore pellet while the chemical reaction goes on at the intermediate level. So hydrogen is getting diffused inside the pellet by diffusion across the product layer and as well as the intermediate product layers of FeO, Fe3O4, and the chemical reactions are occurring at the interface, and basically after chemical reaction, similarly the product which is H2O, that is also supposed to be diffused out. So the overall kinetics in mathematical terms, basically it could be a gas solid reaction which may have the coupled diffusion assisted mass transfer phenomena and as well as the chemical reaction control. So all these studies have been performed very rigorously over the last year, several years, and it is a well-researched topic. And as far as the hydrogen application in the DRI making is concerned, it is also a well-researched topic, and hydrogen can be used up to the level of 100% without any difficulty provided that it is available. So this is you can say that the iron ore reduction kinetics shown at the macroscopic level, at the atomic level, and there also similar kind of phenomena can be observed. I will quickly go in order to just come to the point. So basically this hydrogen can be used in the blast furnace, as our earlier speaker has spoken about some of the efforts which are underway in Tata Steel. So this is the blast furnace reactor, which is one of, you can say, very well known and you can say the most widely used reactor for iron making. So here this iron ore along with the coke, flux containing limestone is added from the top, and the end product is the liquid hot metal, liquid slag. It's a counter current reactor where the top portion, which involves the gas solid reaction, which remains in the solid form, whereas the bottom portion, which is a smelting reactor, and the temperature of the process, I mean to say, that increases as going from the top to bottom. At the bottom level, there is a coal gasification which is occurring, the carbon gasification which is occurring. Carbon is being charged in the form of the coke, and basically so the coal is being converted to the coke in separate coke oven furnaces, and basically that is also highly energy intensive. So overall process is although highly complex and highly energy intensive, but still it is running over the years, and it has achieved a maturity level. It has achieved a level where people have mastered the science and art of iron making into the blast furnace. So that is why it is a predominant route of iron making still today. But it cannot run for a very longer period of time because it is at the same time highly energy intensive also, and you cannot replace the coke also beyond a certain level in this process. But hydrogen can be replaced with the pulverized coal injection to a limited extent, subject to the endothermic reactions, and also it can be further increased by increasing the oxygen enrichment. But if you increase oxygen enrichment beyond certain level, there are increased safety issues and damage to the equipment. And one of the major advantages is that by injecting the hydrogen, because it is endothermic reaction, so the low temperature operation of the blast furnace, it is favorable to reduce the carbon emission by decreasing in the temperature of the thermal reserve zone and heat loss from the blast furnace. In that way, it is going to have an indirect effect. So basically, this is just a representation of the low temperature operation of the blast furnace due to the hydrogen injection, resulting in the low carbon emissions. So what is going to happen is that because of the hydrogen injection, as we can see that some 10% of the endothermic reactions can be replaced by the hydrogen injection, and whereas this in the thermal reserve zone, still the reduction of iron oxide by CO will still continue, but it will continue at a lower temperature, and because of the lower temperature, the utilization efficiency of carbon monoxide will be more, and it will further reduce the carbon dioxide emission. So basically, the whole idea is that hydrogen extends the temperature zone of Brewsterite zone by decrease in the temperature at which Brewsterite reduction is possible. This means that more Brewsterite can be reduced by indirect reduction, and therefore the direct reduction ratio can be increased in this process. Now, I'm talking about the possibility of using hydrogen in this SAT furnace. So the Madras is a very, you can say that well-known and commercially used SAT furnace operation for DRI making across the world. In the Madras, basically we are using natural gas, which is reformed by using the high temperature waste gas coming from the top of the reactor. But at the same time, although the product is the syngas containing carbon monoxide and hydrogen, the hydrogen in the conventional Madras process after the reformation of the natural gas is of the order of 55 to 60%. But if another source of hydrogen or green hydrogen is available, it can go up to the 90% or 100% also as well. So this is the technology which is already available, where the hydrogen can be replaced with the syngas, or hydrogen can be replaced with the natural gas to the 100% level, provided that the hydrogen is available at a higher volume. So one of the possibilities that hydrogen can be used in the Madras process to the 100% extent. Now I'm going to talk about the new developments which are going on this particular area, that is development of a new technology. So one of the technology which is under progress is in the area called as hydrogen plasma smelting reduction process. So basically, in the plasma reduction process, hydrogen, instead of molecular hydrogen that I have seen in the earlier process, it has been injected in the plasma form, that is in the ionized state, where in the atomic form of the hydrogen or ionized state of the hydrogen, it is having better kinetics as compared to the molecular hydrogen, because there are simultaneous action of atomic, ionic, and vibrationally excited hydrogen which are participating in the reduction process of iron oxide. And basically, another advantage is that this process will be a single-step process, eliminating the multiple steps of the other process as compared to the conventional iron steel making process. So this is the schematic diagram of the single-step HPSR process, where this hydrogen can be reduced under the plasma, and in a one-step process, the product will be the crude steel, which just requires a secondary steel making operation. If I look at you can say the free energy graph for the oxidation of hydrogen, or you can say that the hydrogen which can be used as a fuel. So basically, for the ionized state, and as well as as you can see that for the atomic state and for the ionized state, the free energy is further coming down. So the process can be carried out not only at you can say that at lower temperatures also, but at the same time, there's a higher thermodynamic driving force for HPSR process. And if I look at the hydrogen plasma smelting reduction process at the scale of temperature and carbon percentage, and if we compare it with other process routes, we will find that if we compare it the conventional route of say, for example, starting from the ore and then going to the hot metal production in the blast furnace, which is already super saturated with the carbon, and then that carbon is being removed by BOF steel making process, and then it is going to the secondary steel making stage. Lot of steps are there, and in the lot of emissions.
So we're almost run out of time. So we need to stop now and just one or two quick questions.
Okay.
Can we do that?
Okay, and anyway, I just quickly give two more important slides. So if I compare the hydrogen plasma smelting reduction process, it is free from carbon dioxide emission. It is a single unit production for the steel, and basically it is eco-friendly, and iron ore fines can be used. And basically, this is the final slide. So I have talked about the possibility of replacing hydrogen with carbon for various process routes. I have talked about this blast furnace BOF route. So hydrogen can be replaced only to a limited extent, that 15% hydrogen can be replaced in the conventional blast furnace, subject to the oxygen enrichment. If oxygen enrichment can go to beyond a certain level, considering the safety issues, then we can go higher. Otherwise, 15% only the conventional blast furnace. In the DRI production, this technology is already available, and hydrogen can be replaced to 100%. And in the hydrogen plasma smelting process, which is underway to development, and in India, it has been tested to the 10 kilograms level by IMT Bhubaneswar, and we had also signed a MOU with them to work in this area further. So these are the three possibilities by which you can say that hydrogen can replace carbon. So now, because of the shortage of time, I am just stopping here, but I can have further discussions with all. Thank you very much.